of Sriwijaya University, and also the students of undergraduate program of Department of Mathematics Education, Faculty of Teacher Training and Education of Sriwijaya University. Alhamdulillah, praises to Allah Subhanahu wa Ta'ala for all His blessings and gifts, so that we can gather in the postgraduate hall building of Faculty Teacher Training and Education of Sriwijaya University. Salawat and greeting. Don't forget to report it to our great Prophet Muhammad Sallallahu Alaihi Wasallam, who has brought us from the darkness to the brightness like nowadays. I am Cici Rananenci, as a master of ceremony for this event, would like to say welcome to the general lecturer with the theme Continued Fraction Expansions, Monday, 16 October 2023. Ladies and gentlemen, for the first agenda and open this event, it's good for us to say Basmalah, Bismillahirrahmanirrahim. The next agenda is speech from the first Vice Dean of Faculty of Teacher Training and Education of Sriwijaya University, and also officially open this general lecture. To Mrs. Dr. Rita Indrawati MPD, time is yours.
Ruri Tria Astika di Perak Bekti Rahayu dengan konseling Sasti Oktasari BK Alif Bahtiar Pamulang sejak
buka acara.
Alright, the next agenda is speech from the coordinator of undergraduate program of Department of Mathematics Education. To Mrs. Weni Dwi Pratiwi, SPD MSc, time is yours.
Okay, thank you, Cici, for your time. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. The Honorable Speaker, Dr. Cor Krijkamp from TUD, the Netherlands, Technische Universiteit Delft, the Netherlands. Thank you for joining us for this special lecture. Welcome to one of the events held by Mathematics Education Study Program, Sriwijaya University. Dr. Krijkamp was a supervisor of Professor Yusuf Hartono, as we know, and an expert in number theory. So take this moment to learn more about numbers. And the Honorable Vice Dean of Academic Affairs, Dr. Rita Indrawati, MPD, the Vice Dean of Administration and Finance, Dr. Andani Mas Aisyah, MPD, PhD. Thank you for also joining this general lecture. I would like also to say hello to all the lecturers in Mathematics Education Study Program, event committee, and all the students. Welcome to general lecture, Continued Fraction Expansion. And mathematics, I think, can be challenging for you, for all the students, but it's also full of wonder and excitement, including this topic today, continued fraction. It is like mathematical puzzles that allow us to represent numbers in a unique way. They provide insights into the depths of mathematical beauty, and understanding them can immensely rewarding. Throughout this lecture, I think we're going to dive into continued fractions in a way that's accessible and engaging. We'll explore how these fractions work, why they matter, and how they relate to real-world application. To all the students, feel free to ask questions. share your thoughts, and embrace the challenge to learn something new. I think it is not really new because we already have it in our number theory courses, but I think you will get more and more knowledge about this topic. And by the end of this lecture, I hope that you will have better appreciation for the elegance of continued fraction expansion and the role they play in the world of numbers. So let's start this mathematical adventure together, and I encourage all the students to actively participate. Please prepare your question. And to all the participants, lecturers, and especially for our speaker today, thank you for being here, and let's start exploring this fascinating world of continued fractions. Later, I would like to invite Dr. Rita Indrawati as the Vice Dean of Academic Affairs to open this event officially. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you to Mrs. Weni Dwi Pratiwi SPD MSc for this speech. The next agenda is speech from the first Vice Dean of Faculty of Teacher Training and Education of Sriwijaya University, and also to officially open this general lecture. To Mrs. Dr. Rita Indrawati MPD, time is yours.
Thank you. Can you hear my voice?
Yes, ma'am.
ma'am.
Okay, thank you. So I have to go out from the room. Ya, Bu Eni, so sorry. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillahirabbil alamin. Wassalatu wassalamu ala asrofil anbiya wal mursalin wa ala alihi washabihi ajmain, amma ba'd. My Excellency, Rectors of Sriwijaya University, Professor Dr. Taufik Marwa SAMSE, the Honorable Dr. Hartono MA as the Deans of Faculty of Teacher Training and Education, Sriwijaya University, along with the Vice Dean, the second, third Vice Deans. The Honorable, the Head of Departments of Mathematics and Science Education, Dr. Ketang Wiono MPD, the Secretary Kodri Madang PhD, the Coordinator of Mathematics Education Study Program, Weni Pratiwi MSc. What we are proud of the mathematics lecturers and all the students as participants in this public lecture, both those who present online in this virtual Zoom room and those who present offline in the FKIP UNSRI campus. What I respect, our resource person, Dr. Cor Krijkamp from Technische Universiteit of Delft, Netherlands. Welcome to Mathematics Education Study Program, Doctor, at Sriwijaya University, Palembang. It is, thank you. It is a great pleasure, I think, that the excitement that I stand before you today to introduce our distinguished guest speaker for the general lecture organized by Mathematics Education Study Program. Therefore, I'm delighted to welcome to this general lecture. And I would like to say hello to Jerry. Jerry, are you in Netherlands now? To take your PhD? Yes. happy there, right? Yeah. So today we have the privilege of the topic that holds significance in the realisms of mathematics, specifically in the interviewings of words of continued fraction expansion. So before we proceed, allow me to extend a warm welcome to our speaker, Dr. Krijkamp. So I believe he brings a wealth of expertise to illuminate this mathematical concept, unlocking its complexities and practical application. As we embark on this intellectual journey, we'll explore the depth of continued fraction expansions, understanding their mathematical intricacies, and solving the beauty they hold. Yeah, mathematics is beautiful, actually, but many students feel difficult to face mathematics. Whether you are seasoned mathematicians or someone stepping into the fascinating world for the first time. I think this presentation promises insights that will captivate your mathematical curiosity. So without further ado, let's extend a warm welcome to our esteemed speaker who will guide us through the enriching landscapes of continued fraction expansion. So please join me in welcoming Dr. Kraikam.
Thank you very much.
Yeah, you're welcome. So Dr. Kraikam, our dean cannot be here with us. He sent his warm greeting to you. Yeah, and he assigned me to deliver a speech in this general lecture. So ladies and gentlemen, on behalf of the Deans of Faculty of Teacher Training and Education, I would like to thank to Mathematics and Head and Secretary, all invited person, the fellow committee members, and all students as participants in this public lecture. So for your information, Dr. Kraikam, the forms of academic activity held by every study program in our faculty in every semester. So we have to implement the academic activities. So we are lucky to have you in this afternoon to share your knowledge and experience in the mathematics field, especially in the expansion. So ladies and gentlemen, seeing the importance of this general lecture material today, it is hoped that all participants, especially students, can make the best of this opportunity, interact actively with our distinguished speaker. Ladies and gentlemen, I hope this is enough for my remarks to convey. By reciting Bismillah, I represent the Deans of Faculty of Teacher Training and Education, Sriwijaya University, a public lecture entitled Fraction Expansions, Continued Fraction Expansion. Today, 16 October 2023, I officially open. Thank you very much. Wabillahi taufiq wal hidayah. Assalamualaikum warahmatullahi wabarakatuh. Thank you.
Thank you very much.
You're welcome.
Thank you to Mrs. Dr. Rita Indrawati MPD for this speech and open this event. Ladies and gentlemen, to provide sweetness and blessings to our event today, let's pray together. We would like to invite Zaka Hakaoki to lead the prayer. To Zaka, time is yours.
It's me? Okay, perhaps you have to switch off the sound.
Oh no, it's praying.
Assalamualaikum warahmatullahi wabarakatuh. Izinkan saya untuk memimpin kegiatan doa pada hari ini. A'udzubillahi minasyaitonirrajim. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Hamdan syakirin, hamdan na'imin, hamdan yu'afi ammahu wa yukafihu mazida. Ya Rabbana lakal hamdu kama yanbaghi li jalali wajhikal karimi wa azimi sultanik. Allahumma salli ala Sayyidina Muhammad wa ala ali Sayyidina Muhammad. Ya Allah, ya Tuhan kami, pada hari ini kami berkumpul di sini, mengangkat kedua tangan kami seraya berdoa kepadamu agar meminta kemudahan, kelancaran serta berkah darimu. Ya Allah, berkahilah dan tuntunlah acara ini, baik dari mulainya acara ini hingga penutupannya nanti. Ya Allah yang maha pengasih lagi maha penyayang, bukakanlah pikiran kami, mudahkanlah lisan kami dalam berbicara, sehingga apa yang kami dapatkan hari ini dapat berguna bagi nusa dan bangsa. Ya Allah yang maha pemberi, berikanlah kesehatan kepada kami, baik kesehatan secara jasmani maupun kesehatan secara rohani. Ya Allah yang maha pengampun, ampunilah dosa kami, dosa kedua orang tua kami, dosa guru-guru kami, karena hanya kepadamulah kami meminta dan memohon pertolongan. Kabulkanlah doa kami ya Allah. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina azabannar. Wa sallallahu Muhammadin nabil ummi wa ala alihi washabihi ajmain. Subhana rabbika rabbil izzati amma yasifun wa salamun alal mursalin walhamdulillahi rabbil alamin. Terima kasih, wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you to Zaka Hakaoki. Ladies and gentlemen, we would like to invite you to take a picture together. For all the participants in the Zoom meeting, please turn on your camera. The documentation will be led by ICT team. For the ICT team, time is yours. All right, thank you for all the participants. The next agenda is delivery of material by the keynote speaker, Mr. Dr. Cor Kraikam from Technische Universiteit of Telp, and will be moderating by Professor Dr. Yusuf Hartono and Mr. Jerry Araiku MPD. To Mr., time is yours.
Hi, Cor. Hello. Hi. How are you?
Still muted.
I'm doing well.
Ah,
Thanks.
great.
The weather, apart from that, I'm doing well.
They asked me to be your moderator, so you see, I have the special chair. They have special
Again,
chair
because
for me to lead the lecture. Hello, can you hear me?
hard to hear.
Hi,
What did he say?
can you hear me?
Yeah, but it's very faint.
Oh, kecil suaranya.
Pak Yusuf, Pak Yusuf, hello.
Hello,
Dr. Kure can listen to you.
hello, hello. Can you hear me?
Better.
Now we can
Good.
hear you.
It's
Yusuf.
better. Yeah, great.
Yeah.
So, Cor Kraikam is my supervisor, PhD supervisor, and it took me 4 years to learn the continued fraction expansions. And you are lucky to have the first hand to deliver the knowledge. Yeah. Okay, time is yours. Cor, you have 1 hour? Hello?
1 hour. Okay.
You have 1
I
hour.
thought it was more.
And then
Okay.
half an hour for questions and answers.
Okay. Well, anyway, I can always stop. So.
Okay, yeah.
Yeah. Okay. So can I share the screen now?
Sure.
Okay. Let's see if I can get my. Oh, where are my? Yeah. Share. Yeah. And then does it work?
Okay, good. It is. Yeah,
Can I
good.
move that? Yeah. Yeah. Can I start?
Sure. That's yours.
Yes.
Okay. Good morning or good afternoon, or perhaps you can.
Good afternoon from Indonesia.
It's a little bit hard. You don't have headphones, perhaps?
That's okay. I
No.
can hear you directly.
Yeah, no, but you cannot hear the
Oh,
questions.
that's right.
Yeah. Okay. Well, good afternoon. Here it's still morning and a very wet one for that. Thank you for the invitation. This is really very nice. And indeed, I was the advisor of Yusuf, and that was really a pleasure. And I think he was a little bit too modest in saying that it took him 4 years. Actually, what I'm going to tell today is something leading to what Yusuf and many other people worked on. Hopefully, you will get an idea of the field and of some other things as well. So today I want to talk about continued fractions, but actually I want to start with something else. And we all know that 1/3 you can write as 0, dot, and then all threes. And you can, but what does it mean? And you can write a quarter as 0.25, so finite. And 1/8 is 0.125, and 1/7 is 0 dot, and then all these digits you see. So, what does this really mean? What does this expression 0.1428 blah blah blah? What does it mean really? And what happens in this last expansion? Is it finite? Is it infinite? And if it's infinite, in what way? Will it be periodic, or will it be aperiodic? Actually, very simple questions. Any child at elementary school could ask this actually, and we're so used to this quarter is 0.25 or an eighth is 0.125. If we sort of forgot what it means, and what does it really mean? When we write a number between 0 and 1 as 0.A1, A2, A3, with the digits in the sets 0, 1 up to 9, what does it really mean? It means it's a series expansion. And so x is the sum of n=1 to infinity, the nth digit divided by 10 to the power n. So it's a1 over 10 plus a2 over 100 plus a3 over 1000, etc. You see? And this goes on, well, in case of, let's say, √2 minus 1 forever, because that's an irrational number. And in case of a quarter, it stops after 2 steps. And then all the other digits, a3, a4, etc., they are all 0. So why is that? And can this be generalized? And yeah, what do we learn from this? Well, one thing we can see right away is that, and that's what we use every day, if we stop at the nth place and throw away the rest, so all the digits larger, then we have a finite approximation of the number x, a1 over 10 plus a2 over 10 squared, 100, etc. So we get a rational approximation of perhaps a rational or irrational. And well, how do you get it? Well, there are many ways. And today I will mention one way, but there are many other ways. But and there are many, many questions, and unanswered questions actually nowadays. For instance, if you look at the number √2 minus 1, which is between 0 and 1, right? What can you say about its decimal expansion? This is called a decimal expansion, because the base is 10 from decimal. And you could also do a base 2 expansion, so binary. But what do we know about the digits of √2 minus 1, the a1, a2, a3, etc.? Actually, surprisingly little. For instance, well, we know it's irrational, that's by the old Greeks, but we have no idea, for instance, whether the digit 7 appears infinitely often. Actually, it's sort of thought that the expansion of √2 minus 1 is what, so that every block of digits appear with the right frequency. How to prove that? So if you can prove this, you're really famous. Okay. First question, why is the decimal expansion of a rational, right, or at some point starts to repeat itself, so eventually periodic and infinite? Well, this is actually elementary school mathematics. You can do what they call a long division. So you can divide what is under the fraction bar on the one on top. So the numerator will divide it on the denominator, or the other way around. So if you have 1/4, you say, okay, I want to divide 1 by 4. That's impossible. So I borrow a digit. So I get 4 on 10. That goes 2 times. I have 2 left. I borrow another 0, and I can do it 5 times. And you can do this with any rational number, and then you will see, okay, I get rests. And so if one of these rests is 0, it's a finite. And if this doesn't happen, well, there are only finitely possible many rests. So at some point you see the same thing again, and then it becomes periodic. So that was an easy one, but in general, these things are difficult. Now, how do you find the expansion? Well, if we take the interval from 0 to 1, and if we divide it in 10 pieces, from 0 to 1/10, from 1/10 to 2/10, etc., then we say, okay, this first digit tells me in which interval I am. So if the first digit is 0, I'm in the very first, most left-hand interval from 0 to 1/10. If the digit is 1, I'm in 1/10, 2/10, etc. So this determines the first digit. What determines the second digit? Well, if you have the interval where your number is, then you divide it up in 10 pieces. So the length of each piece is 1 over 10 squared. And then you again decide, is it in the first one? Then the second digit is 0. Is it in the second interval? Is it in the third, etc.? And so you can refine and refine and refine. Of course, this becomes very complicated and hard to see, but actually it's a very nice way if you sort of blow up these intervals. And that's what I'm going to do. So what I'm going to do is I'm going to use a map, 10x minus, well, what's going to be the digit. And so if it says 10x minus the floor or entier or whatever you want to call it of 10x. So this number is the integer part of the number 10x. So if x is between 0 and 1/10, 10 times 0, 1, so the floor is 0. And if it's in 1/10 up to 2/10, and 2/10 not included, if you multiply it by 10, it's between 1 and 2, so the floor part is 1. And that's what you subtract. So what you do is you take the interval where your x is, you blow it up by 10, so it becomes length 1, or 1, then you don't have to slide it back. Or it's from 1 to 2, then you have to slide it back by 1 to go back to 0 and 1. If the digit was 2, you go to 2, 3, you slide it back to the unit interval to 0, 1. And then you repeat it and repeat it. So this idea of refining and refining, it's sort of inside the definition of this map. But by blowing it up, you have a better picture of what's happening. It looks like almost like a fractal thing. Okay. So for instance, this integer part is really what is in front of the decimal point. Okay. Now, we can use this map to get this expression, this series expansion. So if we have a number between 0 and 1, we said, okay, the nth digit, so an is the an of x, because we're looking at the number x, is I do 10 times this map n minus 1 applied to x, so this t10 n minus 1, that is applying the map I just gave you on the previous slide, this map. And I applied n minus 1 times, so this is not a number to the power n minus 1, but applying the map n minus 1 times, and then take the floor. Now you might think, whoa, why so complicated? Well, this was the original map. So the map applied to x is 10 times x minus the floor of 10x, and we call this number a1. Now I can bring a1 to the other side. I get 10 times x is a1 plus this map applied to x, and then I divide by 10, and I find x is a1 over 10 plus 1/10 times this number between 0 and 1. So I start with x, and I bring it somewhere in the unit interval again, in the interval from 0 to 1. And then I'm going to do that again. So now I'm going to apply my map 2 times to x. So I do the t of x, that's written here. And so this is not taking the squared, but using the map twice. So by definition of the map, I do 10 times, well, the thing here, the map applied to x, minus the second digit. I bring it to the other side, put things upside down, and I find that this map applied to x is a2 over 10 plus 1/10 times the map twice applied to x. Now you might think, whoa, why would you like to do that? Well, remember we had this. And this map applied to x is actually the right-hand side. So I can like cut it out of the blackboard and put it there. So like this. You see, the map applied to x is actually this a2 over 10 plus 1 over 10 times the map twice applied to x. And now I can sort of get rid of these brackets. And I get a 1 over 10 plus a 2 over 100 plus 100 times t, 2 times applied to x. And I can keep on doing this, actually, as many times as I want. So if I continue in this way and I do it n times, and can be 1, 2, 3, 1,000, 1,000,000, you see, I get like the beginning of the series expansion. That's this a 1 over 10 plus a 2 over 100 plus a 3 over 1,000 plus up to plus an over 10 to the power n plus 1 over 10 to the power n. So this is really small times a number between 0 and 1. So if I sort of delete this last thing, I get a rational approximation of x. And the mistake I will make will be because this number t n times applied to x is in 0, 1, will be smaller than 1 over 10 to the power n. So it's really a small mistake I'm going to make. And if I let n run to infinity, this mistake goes to 0, just disappears. So I get an infinite series expansion. And so I get this, this expansion. Okay, so that's where you can say that's where it comes from. And there are, of course, other ways to obtain this, but to do it in this way, yeah, you sort of, you get extra material, you get extra tools to address what's happening here. And you could bring in tools from ergodic theory, which is like the probability theory of dynamical systems, and then understand what can I say about these digits? How often will I see for almost all x's, or for all x except for a set of length 0, of measure 0? What can I see for digits? And of course, we all know that for a general x, everything is possible, all sequences of 0, 1 up to 9. And well, we can prove that. So we can bear to use the power of the tools of ergodic theory, of probability theory. And we can also do number theory. So this talk will be a mix primarily of number theory, and sometimes I will hint at ergodic theory and probability theory, but most of it is number theory. Okay, now this you can do also. This was base 10. Because I worked with 10 parts. I can work with 2 parts, then it's binary, or 3 parts, or 12 parts, or 6, or 24. And you might think, well, who's interested in bases 12 and 24? Well, I remind you that you use it every day, by the way. The base 6 or 12 or 24 is extremely important. We use it in time. And that's because 6 and 12 and 24 have very many divisors. Nice divisors, 2, 3, 4, etc., 6. So that's what we use every day. And then the same thing works. Instead of r is 10, you can take any r greater or equal than 2, integer, of course, and then you get this is like an alphabet. You can describe any number, actually any positive number in this way. So if r is 2, you only have digits, then you divide your interval from 0, 1 in 0 to a half, and from half to 1. You have only digits 0 and 1, etc. And we all know it's actually extremely powerful. It's more or less doing the same. Okay, and then you get an expansion like this, which is written here at the base. Okay. And in base r, you have the same thing as in base 10, in general base r. Almost all numbers are unique except some rationals. For instance, if r is 10, then you know that if you have a rational number and you divide by something which is not a power of 2 times a power of 5, then it will become periodic. But rationals have measure 0. If you look at the length inside r of the rationals, the Lebesgue measure, then it's 0. All other numbers have a unique expansion. For instance, a number which has 2 expansions is a quarter in base 2, and you can write it as a quarter is a quarter, 0 divided by 2 plus 1 divided by 2 squared, and then the rest is all zeros. But you can also write it, this 1 quarter, you can write it as a half time a half, and this you can write, so you can write as 0 divided by 2 plus 0 divided by 4, and then all the other digits will be 1. So there are 2 expansions. And at school, you learn that you should never use the second expansion. Okay, that's just a thing we sort of decided to do. Of course you can use it. There's no golden rule here. Okay, now, many things have finite expansions. So all these things, they work for a general positive integer larger than 1, of course. But then you can wonder, and I'm not going to talk about it today because I could give an entire talk on this. What happens if r, this number r, this base, what we took 10 for binary or 24 or whatever, what if this base is, but not in n, and the base should be larger than 1? What will happen? Well, I can tell you, things will be really very different, spectacularly different. And suddenly, Lebesgue is not the world we're in anymore. Suddenly, all kinds of things happen with your digits. Some things are forbidden. For instance, if your base R is the golden mean, so root 5 plus 1 over 2, 1.6. If you do that, and you have an expansion of a number, then you will never see two consecutive ones. Never. That's spectacular. Suddenly, the whole landscape changes, and that's actually not so studied for a very long time. I mean, these are beta expansions. In such a base are usually called beta, except by Erdős. He calls them Q. Why? But these are from the 1950s, end of 1950s, 1960s, and from that moment on, they have been studied very intensively. I could give a talk on that, but I'm not going to. I think my wife is giving a talk soon, and she will talk about this in Indonesia online. But it's really nice. But I want to talk about continued fraction. So that's a totally different way to expand numbers, to deal with numbers. And let me go back in history some few thousand years and remind you of the divisor or Euclidean algorithm. You must all have seen it, I suppose, or it's really easy. I mean, you could sort of come up with it on the bicycle or while taking a shower or preparing a meal. What is the idea behind this algorithm, which is still used up to today? It's an important algorithm also in computer science, surprisingly. In spite of the fact that it's so easy. Suppose I have integers a and b, and let's assume, because it doesn't really matter, that a is larger than b and b is positive. So b is larger than 0. What can we do? Well, I call a is R0, b is R1. So the r's are in size. And I'm going to determine a number a1, which is sort of like a digit, and R2, which is sort of like a rest. Notice the a1 is a positive integer, so it's a natural number. It's 1, 2, whatever. Is a non-negative integer. It's an integer, but it might be 0. And what I'm going to do is I'm going to write the larger number, R0, as a1 times R1, but R2 is going to be smaller than R1. So I'm going to fit R1 as many times as possible into R0. So suppose R0 is 21 and R1 is 5, then A1 is going to be fitted 4 times in there, not 3 times, because then the rest would be 6 and would be larger than R1. Now I want to put it in there as many times as possible. And not too many, I don't want it to stick it out. So this rest is going to be positive, but smaller than R1. Now, it's possible that the rest is 0. Then I'm done. And then actually R0 was equal to some positive integer times R1. Yes, for instance, R0 is 20, R1 is 5, 4 times 5 is 20. Easy. And then R2 is 0. The rest is 0. There's no rest. Okay, but let's assume that for the moment the rest is not 0, then I can repeat it. If it's 0, I'm done. But if 0, I can repeat it. And then I'm doing the same thing, but you see that these rests, which are positive integers or 0, they are decreasing. So you know at the finite number of steps, I must hit 0. So this procedure, which is the Euclidean algorithm, must at a time. And the maximum number of steps is, of course, R1. So that's very funny. It's a very simple algorithm, powerful, and yeah, I don't know, but it's quite beautiful. And so there is a positive integer such that Rn is not 0. If I read the next one, bang, is going to be 0. And so for all the previous case, I have this expression. Rk is, I can fit rk plus 1, ak plus 1 times in rk, and I get a little rest. That's rk plus 2. And then at some point, bang, the rest is going to be 0. That's here. The Rn plus 1 must be 0 because this is a decreasing sequence of non-negative integers. You're bound to hit 0. That's impossible. And then the algorithm stops. And well, what we learn, at least what I learned long ago, is that the greatest common divisor is then Rn of A and B, of R0 and R. So this is the algorithm, but actually I want to sort of put it upside down. So I want to say, note, was the number of times I could fit R1 in R0. And so it's the floor of R0 divided by R1. So for instance, if R0 was 21, 5, 21 divided by 5 is 4 plus 1/5. This entier or floor things sort of keeps only the integer parts, so the 4, and etc. For all these other guys, you do the same. Aha, okay, that's nice. And I'm going to now set, okay, x is the number R1 divided by R0. So this is a number between 0 and 1. And then T1 is R2 over R1, and I repeat this. So Tn minus 1 is Rn over Rn minus 1. Okay, and the last one would be Rn plus 1 over Rn, but Rn plus 1 was 0, so Tn is 0. You might think like, why would you do that? Now, note that 1 over x is R0 over R1. That's sort of stupid. But R1 we know, R0 we know is A1 times R1. We could fit R1 A1 times in R0, plus the little rest. Well, I can divide this out. So this is A1 plus R1 over R2 over R1. Hey, I call this T1. Oh, but 1 over T1 is R1 over R2. And R1 was the number of times I could fit R2 in. I could write R1 as A2 times R1 plus some rest. So I can divide out again. I get this. And I can keep on doing this. And the last one, I would get, well, this Rn plus 1 is 0. So I can just divide out and I get A1 plus 0. Now you might think like, okay, so what's the use of this? Well, all of these numbers, 1 over x, 1 over T1, 1 over Tn minus 2, 1 over Tn minus 1, I'm going to put them upside down. So I'm going to do 1 divided by these numbers, so they will turn around. So I will get x is 1 over A1 plus T1. And I would get, if I would turn the other one upside down, T1 is 1 over A2 plus T2, and this goes on. T2 is 1 over A3 plus T3, all kinds of fractions. So the ith one would be Ti minus 1 is 1 over Ai plus Ti, and this goes all the way. So this is the last one. This was this 0, this Rn plus 1. But now we see something nice. We see that x is 1 over A1 plus T1, but T1 is a fraction. So I can sort of take this fraction and put it in the position of T1. So I would get 1 over A1 plus 1 over A2 plus T2. Aha, but T2 is again a fraction, so I can replace this T2 by this fraction 1 over A3 plus T3 and just plunk them in, one by one. And if I do this, I get, well, the first one was 1 over A1 plus T1, but T1 was 1 over A2 plus T2. Look, and I can just keep on doing this until I get this weird-looking object, and this is a continued fraction. This is a finite, regular continued fraction. And by the way, Euclidean algorithm sort of yields, you can see that this an is 2 or more. Aha, so continuous fractions, although probably they didn't realize it, were already known by the Greeks thousands of years ago. Okay, they had the algorithm. If you put it on top of on its head, then it rolls out, so to speak. So this is a finite continuous fraction. And actually, every rational number in Q can be written as such a finite continuous fraction. You can take this A0 and a naught is such that x minus a naught is between 0 and 1. So that's the integer part of it, so to speak. And then with x minus a naught, which is in 0, 1, you can do the procedure, just solve, and you get this fraction. Plonk. It's easy. Okay, and this is very annoying to write down, even to type in LaTeX. So we write it like this. It's a kind of decimal notation, but different than the decimal notation, so it cannot be sort of mixed up. But I mean, nobody liked this expression to type because it's really annoying, but you can write it like that. Okay. So actually, because this an is greater or equal than 2, I could replace an by an minus 1 plus 1 over 1. So I can make it a little bit longer. So in case of a rational number, you actually have 2 expansions. One which doesn't end with a 1, and one which ends by 1. You can the left-hand part is due to the Euclidean algorithm. The an is not 1. It's 2 or more, but you can sort of subtract 1 from an and do so an minus 1 and then plus 1, but the plus 1 is written like 1 divided by 1. So that's why you have 1 extra click. This is just handy for proofs. I mean, nothing deep. But it's not unique, that's my point. But this is only for rationals. You might say like, okay, what's happening? Well, notice that we had this. And the ti minus 1 was 1 over ti plus ai, or 1 over ai plus ti. That's what I wrote. And this is the same as writing ti is 1 over ti minus 1 minus ai. Actually, I had this first, and then I got this thing. But this we could sort of use to generalize this whole idea. So instead of looking at rational numbers, we could just take, for the ti minus 1, well, why not sum x between 0 and 1? And then what would ai be? Well, that would be the floor of this 1 over x. If I take for so this immediately begs for generalization. Like, please generalize me. Do something for all x between 0 and 1. So that's what we're going to do. Yeah, so I define now a map like the decimal map, but it's not going to be linear. The decimal map is linear, 10x minus some digit. That's not what we're going to do. It's not a linear map, so things are more difficult, certainly from the point of view of probability theory. We're going to define a map. I'm just calling it T. It's going to be the regular continuous fraction map or Gauss map in the following way. I do this 1 over something, 1 over x, minus, and then the digit is to bring it back to 0, 1. And so if you have an x in 0, 1, 1 over x will throw it out, and then subtracting the floor part will slide it back into the unit interval. That's what's happening here. That's so if your x is between a half and 1, 1 over x will be between 1 and 2, and by subtracting 1, you bring it back to 0, 1. If x is between a third and a half, then 1 over x will be between 2 and 3. Subtracting 2 will slide it back between 0 and 1, etc. So we have digits 1, 2, 3, 4, 5, 6. Actually, any natural number will be a digit. And so this is dramatically different from the decimal expansion. Now suddenly I have a digit set which is n, the natural numbers. It's infinite. Very different. And the maps are not linear, but fractional linear. I will come back to this in a moment. Okay, well, I didn't make a drawing of this thing, but you can sort of easily draw it. 1 over x is easy to draw. I see there is a blackboard behind me. It looks like, let's see. Well, someone wrote something on this, but it looks like this. So this is a half and 1, and it looks like I is 1 over x minus 1, and between a third and a half, it looks like this, and etc. Well, it's not clear whether you could see this, but well, you can also do it yourself. It's not hard. To be honest, I was typing all of this, so I didn't have any more time to put this in things. Sorry. Okay, of course, T0 is 0. We have to do something with 0. We just demand it stays on its spot. Okay, and this is what is known as the Gauss map, continuous fraction map. And there's a reason why it's called the Gauss map, because Gauss made incredibly important contributions to the theory of continuous fractions. I mean, Gauss made extremely many contributions to very many parts of mathematics, but certainly here. Okay. Now, suppose my x is in 0, 1, and for which I didn't land there, so I repeat my map n-1 times, and I didn't land on 0. By the way, the Euclidean algorithm tells you that if x is irrational, there is an n that you will land on 0. You will get a finite expansion. You will walk around, and if your x is rational, there's a moment that this Tn-1 of x is going to be 0, and then you will stop. Note, by the way, that if irrational, then 1 over x is irrational, and subtracting a positive integer will not change that. This map T applied to an x will be irrational, will not be a rational number. So you using this map T as many times as you like, you will never land on 0. So it just keeps moving. You could, as an exercise, try, for instance, root 2 minus 1, and then you will see, for instance, I will get the digit 2 all the time. This is a fixed point. This is mapped to itself under this map. So all the digits will be 2. So root 2 minus 1 will be 1 over 2 plus 1 over 2 plus 1 over 2 forever. It will go on forever. Okay. So if x is irrational, this will definitely happen for all n. Okay. And that's what I write here. And now I'm going to define simply this 1 over Tn-1 times applied to x, and then I throw everything away behind the decimal point. So it's just the integer part. Okay, and I'm going to do actually the same kind of trick, whatever, the decimal expansion. And so the t of x is 1 over x minus a1. I can bring the a1 to the other side. So I get x is 1 over x is a1 plus t of x, and therefore so let me go back to the map. And this is a1, this entier of 1 over x. So I have the t of x is 1 over x minus a1. If I bring a1 to the other side, I get 1 over x is a1 plus t of x. So x is 1 divided by that. But you can see it here. X is 1 divided by a1 plus t of x. And in the same way, the t of x, a2 plus t 2 times applied to x, etc. So the t n minus 2 of x is 1 over a n minus 1, the n minus 1 digit, plus t n minus 1 times applied to x. And if x is rational, at some point you have a 0 there. If x is irrational, this holds for all n. Okay. So what is nice is I can sort of do the same trick. I can say x is 1 over a1 plus t of x, but t of x is 1 over a2 plus the t twice applied to x. So I can sort of take that thing and put it in that spot. So I get x is 1 over a1 plus 1 over a2 plus 1 over, and go on like this. So I get like this, you see. This is x. 1 over a1 plus the t of x. This t of x are replaced by 1 over a2 plus t twice applied to x. And I can go on as many times as I like. Okay. Note that if I remove this t n times applied to x, then this is certainly in general not equal to x, except if this t n times applied to x is 0. But in general it's not, if x is irrational. So if I remove it, if I would remove this t n times applied to x, the right-hand side would be a rational number. And this rational number gives an approximation of x. Actually, we will see an extremely good approximation. Much better than expansion can give you. And that's the reason why we will look at these expansions. One of them, still nowadays, one of the most important reasons to use continued fractions is that you get extremely good approximations by rationals of numbers x, which can be rational or irrational. And this is actually not something which is from today or yesterday, but this is quite old. Yusuf probably can recall that in front of this building, you also know that there's a statue of Christian Huygens, which was a Dutch scientist from what we call golden age, although nowadays the whole idea of this golden is becoming a little bit shady, but okay. And this guy, fractions on rationals, mind you, or also on irrationals, to get rational approximations of irrational numbers. And he had to use this because he was building for the French king, for Louis XIV, the Sun King. He was using a planetarium. So one of the, I think the premier or one of the ministers of the king asked him to build such a thing. It still exists. It's just a box. And then you see in the middle the sun and the planets around it. And it's actually a clock, right? I mean, it can only be a clock. It's just running. Yeah? So the Earth is moving in 1 year around the sun. Of course, it goes a little bit faster. Otherwise, it would be really boring. And all the other things are also moving in their own, are like rations, which are irrational, of the sun. And he had to approximate this, and he had to build a clock, really. He had to approximate these irrational numbers by rationals. And the teeth of the clock are really the rational numbers, the number of teeth. And so he had to come up, actually, this idea is due to Huygens, to use these expansions to find the best possible approximations in rational numbers of irrational numbers. And you could try something, but actually these guys, they are top. And he proved that also. So he developed this theory just to build this thing. Can you imagine? It's actually very funny because at some point Holland was at war with France. And he was working for the French king. He was actually the president of the Académie des Sciences, so the scientific whatever academy or whatever. But he had to stay in Holland because of the war. And well, he had this thing built. It was actually quite expensive for those days. But then he couldn't ship it to France. And at some point, the prime minister died. So it was another prime minister was not interested in this thing anymore. So it's still in Holland. You can see it in Leiden, in the Boerhaven Museum. So many people look at it and think, a box. But it's actually very important, a very nice, a very beautiful planetarium. In Holland, the most famous one is in the north. It's very spectacular. This is not so spectacular looking, but the mathematics is actually quite spectacular. And the one in the north, did you ever see it actually? No. You never went to Franeker, right?
No.
That's a pity. You should go. It's spectacular planetarium. It's a guy built it in his bedroom. It's really beautiful. Not the thing of Huygens. It's just so that's why we do this. And then you might wonder, what happens if n tends to infinity? Do we have convergence of some kind? And yeah, well, we do. And actually, I'm going to show that. And well, because we have convergence, we write it like this, but this is a very unpleasant notation, so we write it in the other notation. Anyway, what do we mean by this convergence? We mean this, that if you take Pn over Qn relatively prime, such that this is this finite continuous fraction, then x is equal to the limit for n tends to infinity of these rational numbers. So these rational numbers, they converge to x. That's why they're called convergence. Okay. How can you see this? How can we prove this? How did Huygens see this? Well, he was a really brilliant guy. So, well, there are really many ways to show this. And, well, I'm going to use one way, which is called Möbius transformations, which is sort of nice because you all had probably linear algebra. And this is extremely simple use of linear algebra. So this is very, very nice I mean, the math itself is usually not so hard. It's more cleverly put together. So we're going to look at matrices with entries from Z, so integer entries. And it sounds very posh, SL to Z. Well, it means that the determinant is plus or minus 1. And so I'm going to have entries which are from Z. And if I do A times D minus B times C, it's going to be plus or minus 1. Okay. Actually, I'm going to attach to such a matrix a special map, which is a fractional linear map. Fractional linear because it's a fraction, and in the numerator and denominator, there are two linear transformations. And so if I have A, B, C, D, I'm going to write A applied to X. People in algebraic geometry would write A dot X, but okay. I see it as a map, so I write it's A times X plus B divided by C times X plus D. Of course, if X is minus D over C, you get infinity, so that's why X is in R plus infinity. Okay. And that's known as Möbius transformations, and you can use some linear algebra to show that, well, if A and B are in SL2Z, so if they are of the form A, B, C, D, and A, B, C, and D are integers, and the determinant is plus or minus 1, then the product, of course, is also of determinant plus or minus 1, and all the entries are again integer. That's easy. But something else is nice. If I do A times B, so that's a new 2x2 matrix, which is SL2Z, and I apply it to X, that will be the same, actually you need to prove this, as A applying to B applied to X. This looks trivial, but it's a little bit writing out. It's not hard, but this B of X is small a times X. Well, I don't know what B was. Let's say C and A, K, L, M, N, and well, you write it out and you will see it happening. And you might think, why are we looking at these things? Why is this interesting? Well, that's a good question. Suppose X has this continuous fraction expansion, and I'm going to define special matrices. AN is 0, 1, 1, AN, for n is 1, 2, 3, 4, etc. I'm assuming I have an infinite expansion, otherwise it's finite. And Mn is just going to be the product from 1 up to n of A1 times up to AN. So the product is these guys. Note that these have determinant minus 1. 0 times AN, that's 0, minus 1 times 1. So Mn has determined minus 1 times minus 1 times minus 1 times minus 1 is minus 1 to the power n. That's an important thing. It's trivial, but important. And what do we have? Well, if I apply this matrix to 0, I get 0 times 0 plus 1, which is 1, divided by 1 times 0, which is 0, plus AN. So I get 1 over AN. And if I apply AN minus 1, if I do AN minus 1 times AN and apply it to 0, it's the same as applying AN minus 1 to 1 over AN. And recall, this is going to be 0 times 1 over AN, which is 0 plus 1. So it's going to be 1, divided by, well, 1 times plus AN minus 1. So it's going to be like this. And you see the tail of the continuous fraction is starting to appear. So if I continue in this way, so a kind of finite induction, I see that I get the continuous fraction, the finite, the approximation I get, the convergent I get. And so the Mn applied to 0, the matrix seen as a Möbius transformation applied to 0, gives me the convergent. Oh, isn't that cute? Oh, surprising. Oh. Now I'm going to write this matrix as, let's say, Rn, Sn, Pn, Qn. I just give them names. Matrix in SL2Z, so Rn, Pn, Qn, Sn, these are integers. And the determinant we saw is minus 1 to the power n. And then you think like, yeah, I get something from this. Well, notice that Mn is A1 times A2 times up to An. So I can take the first part from A1 up to An minus 1. Well, this multiplication, this is Mn minus 1 times the last one. I can just plug this in. Mn minus 1 is Rn minus 1, Sn minus 1, Pn minus 1, Qn minus 1. There it is. And the last one was 0, 1, 1, An. Oh, well, linear algebra. This is a very easy multiplication. So I get Pn minus 1, Qn minus 1 as the first column of Mn. So I see that Rn is Pn minus 1 and Sn is Qn minus 1. And I see the second be An times Pn minus 1, this times this guy, plus Rn minus 1. But if Rn is Pn minus 1, then Rn minus 1 is Pn minus 1. And Sn minus 1 is Qn minus 2. Oh, wow. So I get a lot of structures suddenly. That Rn is Pn minus 1, so Rn minus 1 is Pn minus 2. Sn is Qn minus 1, so Sn minus 1 is Qn minus 2. And I get what they call, I already had this, by the way. I'm coming back to this in a second. Because of this, what I'm writing here. But I also see that the Pn's and the Qn's satisfy really nice recurrence relations. And this is very handy if you want to calculate the convergence, really. If I have like root 2 minus 1 is 1 over 2 plus 1 over 2, and I stop it somewhere by hand to sort of roll back and see what the convergence is, very hard. But if I have these relations, it's peanuts. I can just see 2 times 0 plus 1 is 1. And Q1 is 2 times 1 plus 0 is 2. So the first convergence of root 2 minus 1 is a half. So root 2 minus 1 is approximately 1.5. That's a bit stupid, but I mean, as a first one. And P2 would be 2 times P1 plus P0. That would be 2, and the other one would be 5. So I would get as a second approximation of root 2, 1 plus 1/5. So 1.4. So this goes quite quickly. So actually to have these things is extremely handy to get the convergence. And now going back to this, note that suppose that Pn and Qn had a divisor in common, so that they were not relatively prime, they were not co-prime. So suppose there is some d which is the divisor of Pn and of Qn, and P larger than 1. Then it would be left-hand side automatically because it's the divisor of Pn and Qn. But then it would be a divisor of minus 1 to the power n, which is plus or minus 1. So it would be a divisor of 1. Impossible. So Pn and Qn are automatically co-prime. So you get really, right away, very nice numbers. Very nice approximations. For free, really. The whole setup makes things easy. Now, you might become greedy and say, okay, so I know Mn applied to 0 is this approximation. It's of course, because this matrix was Pn minus 1, Pn for the first row, Qn minus 1, Qn, and if I apply it to 0, I get Pn over Q. But actually I want an expression for x. Well, for that I define a new matrix. I replace An by this guy. Instead of having just An in this lower right hand spot, I put An plus Tn times applied to x. Because then I know that x is actually, if I multiply this out and apply it to 0, this would be 1 over A1 plus 1 over A2 plus 1 over up to 1 over An plus Tn. If I apply it to x, so this is x. But I can also use linear algebra now. I know what Mn minus 1 is. I know what An star is. I can just multiply it out. This is Mn minus 1. If I multiply it out and I apply it to 0, I get x is this expression. This looks like horrible, but it's not so bad. In the beginning, you think like, ugh, this is totally useless. But actually, it's quite useful. And if I have this expression, I can look at x minus Pn over Qn. And that's what I want to do. This determinant is plus or minus 1. We can look at x minus Pn over Qn. X is what we just saw. So this expression. So I can put this expression Pn plus Tn times applied to x times Pn minus 1 divided by The same thing for q's. I can put it on the place of x and can make what we're dividing by the same. So I get qn times this thing here. And note that this comes from x. And then what's up here is just permanent times t and times applied to x. So if absolute value of x minus pn over qn, so how far is my convergent pn over qn from x? That's the absolute value. Then I get here, the minus signs drop out, t n times applied to x, which is divided by qn times, oh wow, this is larger than 1. So I could take a qn out, I would get qn squared times 1 plus etc. This is more than 1. If you divide by it, it's going to be smaller than 1. So I find this, x minus the convergent, so the distance from the convergent to x is smaller than 1 over qn squared. Now you might think, wow, not so impressive. Well, you are mistaken. Because these qn's, they satisfied this recursion relation. And the qn was an times qn minus 1 plus qn minus 2. And the an numbers, natural positive integers. And suppose they are all 1. That would be the slowest case. Then these qn's are the Fibonacci numbers. So 1, 1, it's always the sum of 2 is the next one. So 3 plus 5 is 8, 5 plus 8 is 13, etc. Your ANs, your digits are all 1. So you really add up 2 of the 2 consecutive Qs to get the next one, so to speak. This is the slowest growing sequence. It's growing exponentially. So you really get approximations. And by the way, from this, it's actually trivial, because these qn exponentially, qn squared is even worse. 1 dividing by the thing, bang, flies to 0. So you have convergence, but we have much. For instance, what we have is that these converge around x because of this minus sign. This is minus 1 to the power n. You go under, over, and you move to. That's very nice. The decimal expansion was approximation from below, because you get a series expansion and you leave out the last part, the 1 over 10 to the power n times t n times applied to x. Then here you jump around, and you converge to x. Okay. So this is one of the important reasons to look at continuous fractions, and there are many people who looked at this. Just to name a few incredibly famous people, Dirichlet, Horwitz, Legendre, and let me mention the one and give us a quick proof of it, although it's really old, 1842. Dirichlet was an incredible mathematician. Well, let x and q be real numbers, and the q is larger than 1. Well, you might assume that it's actually an integer larger than 1, so 2 or more. And then there exist 2 integers, and q is a positive integer, a number greater or equal than 1, but smaller than this capital Q, such that the distance p over q, 2x, so the absolute value of x minus p over q, this is going to be smaller than 1 over small q times capital Q. For every q, you can find such a fraction. Okay, this is a very simple result. And continued fractions sort of pick very special p over q's, which are really powerful. How to prove it? Oh, well, let me give a quick, because I haven't given any proof in a way up to now. See that now I'm busy for an hour. Suppose that we can assume that the q, as we can take just the floor of q plus 1, q star. It's a little bit bigger than, but an integer, and work with q star. So we can assume it's an integer, and we're going to work with the so-called pigeonhole principle. And the pigeonhole principle is very simple. if you have n plus 1 pigeons, say 11 pigeons, and you have 10 boxes, n boxes, then there will be if you want to put them all in a box, then there will be at least one box with 2 pigeons. You cannot avoid that. That's the pigeonhole principle. Sort of obvious principle, right? But anyway, and that's what we're going to use here. So we're going to look at q plus 1 numbers, 0, well, it's a number, 1 times x, and then we throw away its integer part. So this is the fractional part of x, everything behind the decimal point. So it's in 0, 1. 2 times x, its fractional part. So you throw away the integer part. 2 times x might be larger than 1. And then what is in front of the decimal point we throw away. 3 times x, its fractional part, up to q minus 1 times x. Q might be 100 million. You can take anything you want. It will stick out of 0, 1, but we look only at the part behind the fractional part. And then 1. So these are all numbers in 0, 1 closed. So 0 and 1 participate. They're indeed q plus 1. This is the first one, 0. This is the second times x fractional part, etc. Okay. What's the idea? We divide 0, 1 into q subintervals of length 1 over q. So from 0 to 1 over q, from 1 over q to 2 over q, 2 over q to 3 over q, etc. These guys. And I take them right open. Not that it's very important, but anyway. And the last one is completely closed. Okay. And what is now the idea? Well, either one of the following q minus 1, so the fractional part of x, 2x up to q minus 1 times x, its fractional part. This either lives in the first or in the last interval, so from 0 up to 1 over q, or from q minus 1 over q to 1. And if it's not, well, then, and then we're done, by the way, moment y. Or, well, then we suddenly have q minus 1 intervals where we want q minus 2 intervals where we want to put q minus 1 numbers. So 2 should be in the same interval. So if it's in the first interval, if one of these numbers if one of these numbers is in the first interval, what's happening? Let me go back. Then actually 0, I get the fractional part of some q times, some small q times x is in here. So the fractional part is going to be like the small q times x minus some p, which would bring it in 0, 1. And then you look at the distance to 0, so qx minus p minus 0 in absolute value, because it's in this interval, is going to be smaller than 1 over capital Q. And you're done. And the same here, but then you look at the distance to 1. Okay? So that's why, if that happens, if one of them is either there or there, you're done. And so we can just sort of forget about that. It's already done. And then we can look at the other guys, and there are Q minus 2 of them. And we have Q minus 1 points. So there should be 2 where there should be 2 which are in the same interval. And so I have Q1s and Q2 different. Let's say Q1 is larger than Q2, and I assume Q1 is smaller than capital Q, which I started with. And it's just in the statement, given some capital Q, and Q2 is positive. Such that, oh, I'm pressing on the wrong thing, such that Q1 fractional part and Q2 times x, its fractional part, so throwing away what is before the decimal digit, are in the same interval. So in the interval either from 0 to 1 over q, well, okay, that's the case we dealt with, from 1 over q to 2 over q, from 2 over q to 3 over q, etc. 2 of these guys are in the same interval. And this fractional part really is nothing else than there exists some integer such that the fractional part of q1 times x is q1x minus p1. And the fractional part of q2 times x is nothing else than q2 times x minus p2. And they're in the same interval, so the distance between these 2 points is smaller than 1 over q. But then you say, oh, but then I can rewrite this. I can rewrite this as the absolute value of q1 minus q2 times x minus p1 minus p2. And so if I define q as q1 minus q2 and p as p1 minus p2, this thing here on the left-hand side is nothing else than the absolute value of qx minus p. It's going to be smaller than 1 over q, and I'm done. You see, because I can now divide left by 1 over q, I would get x minus p over q, and I would get on the right-hand side 1 over small q times capital Q. Boing. Okay, there you go. I mean, this is by Dirichlet, and really one of the top mathematicians of all times. And you see, well, it's actually not that hard. It's easy, actually. I mean, it might have been a little bit fast, but this is recorded, and I suppose you want to have the slides, right? So you can also read this. It's really a very nice proof in the sense of very in your face, very conceptual. What's happening is really constructive. You feel like, ha, it's well built. I don't know if Dirichlet did it like this, but this is the way I learned it from my advisor, who is mathematically speaking the grandfather of Yusuf as an advisor. Okay. So I gave a proof of this, but okay, this is a bit old stuff. But as a consequence, you see that every irrational number has infinitely many nice rational approximations. And I can, yeah, what we just saw for continued fraction convergence holds in general. Okay, but you can always do better. So like one of the Hurwitz brothers showed, I forgot which one, probably Arnold Hurwitz showed that if you have an irrational number x, then you have infinitely many q, relatively prime. You don't need to demand that because, I mean, if it's not relatively prime, the result only gets stronger. It says that the distance from the rational number p over q to the irrational number x, so absolute value of x minus p over q, is smaller than 1 over root 5, which is much smaller than 1. It's 0.4, etc., times 1 over q squared. So Hurwitz sort of cranked up this enormously. And we will see that we can actually show this with continued fractions. We can do actually much better. And that's what we're going to see actually. Okay. Now you might think that there are not so many p over q satisfying this. Perhaps, well, in very sparse. Not at all. Really very many. And that's the strength of these continued fractions. A lot of very good approximations. And well, there are two theorems which testify of this. The first one is by Legendre. This is a bit strange to write year 2 of the French Revolution, but Legendre, when he published this, he really wrote year 2, so the second year. And then it sort of got lost because after the revolution there was the terror. Got lost which year this was exactly. Yeah, as you know, after the revolution, they started to behead with the guillotine so many people that it became really very terrible. Legendre survived, and he wrote at that time this theorem. He came up with it. I'm not going to prove it, although it's not so hard, but it's also an old thing. So let x be an irrational number. Suppose we have p and q in z, so integers. Q positive, relatively prime, so they don't have a common divisor except. Okay. And suppose that the distance from p over q to x, so x minus p over q in absolute value, that's the distance, is smaller than 1/2 times 1 over q squared. This is before Hurwitz, don't forget that. And so 1/2 is more than 1 over root 5. And 1/2 is 0.5, 1 over root 5 is 0.4. But anyway, if you have it, so if you have that this distance is smaller than 1/2 times 1 over q squared, then automatically, that's his result, then this p over q is a regular convergent, a continuous fraction. And so there's a non-negative integer n, such that p is pn, q is qn. Bang! So what does this theorem says? It looks not so, it looks a little bit innocent, but it's actually an incredible term, it says that if you want to approximate an irrational number x by a rational number, and if this rational number p over q satisfies this statement, bang, and this is sort of approximating your number well, then automatically you have a convergence. And so it's almost impossible to escape the regular continued fraction. If you want to do well, you have a convergence. And then you might think, okay, but perhaps this doesn't happen so often. Well, we will see that it's actually. I'm missing now. Oh yeah, Hurwitz is here. That was this statement. So just for rationals, I'm going to prove this Hurwitz, not Legendre, for continued fractions. And you can do this in many circles, continued fractions. There are many ways. Usually they're related to one another. It's really beautiful. This is very classical. And then there was a result by Borel. And what did Borel say? Well, if I have a number x and let Pn minus 1 over q minus 1, Pn over q, and Pn plus 1 over q, three consecutive regular convergence to the irrational number x, then at least one of these three satisfies 13. And what was 13? Let me show you. That's Hurwitz. So one of these three, so Pn minus 1 over Qn minus 1 is smaller than 1 over root 5 times 1 over Qn squared, Qn minus 1 squared, or Pn over Qn here is smaller than this distance, or the Pn plus 1 over Qn plus 1. So for any three convergence, regular convergence, continued fraction convergence, this holds. If you have just three and you have infinitely many, if your x is irrational, just take any three and this will be true. Actually, and for one of the three, this. Okay, wow, not entirely in this way, but that's a result. Tong, Ying Cheng Tong. So in order to get a little bit grip on these things, I'm defining what are called approximation coefficients. Recall x minus Pn over Qn was smaller than 1 over Qn squared. So this number is smaller than 1, this theta n. And I want to have a grip on them. So that's what I'm going to do. And the first result, unfortunately by a guy which turned out to be a party member, but okay, nobody's perfect, 1895, is that the minimum of two consecutive thetas is smaller than a half. And the result of Hurwitz stated that the minimum of three consecutive thetas is smaller than 1 over root 2. Okay. Now, this is what I want to prove. That the minimum of three consecutive thetas is actually smaller than 1 over the nth plus 1 digit squared plus 4. Note these digits are natural numbers, positive integers, so 1, 2, 3, 4. So the smallest possible digit is 1. So this is 1 over root 5, largest possible number, because then you divide by the least. And so this immediately implies Hurwitz. Yeah, because an can be really big. You're going to have a very large digit, and this is an extremely small number. So more or less 1 over n plus 1. Okay? So, but this is a much more general statement. Unfortunately, the maximum is larger than that. So this was found in 1984. So you see, okay, for you guys, probably this is were born, but for me, this is sort of recent history. Many people prove this result. Many. There are many different proofs of it. There is only one guy who came up with this last result, is 15. It's Tong. He's a Chinese guy who moved from China to Florida. But I sort of stopped publishing, but perhaps he's too old now. There are really many proofs, and I will give one, which is, I hope, handy for you. It's just ideas, pictures, really, what's happening. And it sort of is also like a pathway into other things. Now note that we saw that x minus Pn over Qn in absolute value was Qn squared times this fraction, 1 over Qn squared times this fraction. So I can write my theta n like this, Tn x divided by 1 plus Tn times applied to x, this fraction Qn minus over Qn. Okay, well, this looks horrible, right? Wow, what the hell? How can we do something with this? We can do actually a lot because we have recurrence relations for the Qn's. We had this, remember? We said, okay, if we define Qn minus 1 to be 0, Q1 to be 1, then these Qn's, denominators, they can be obtained in the following way. As soon as I know the expansion, I know the Q's and also the P's. So I know the convergence. Aha, but this Qn minus 1 over Qn, I can do something with it. I can say, okay, what can I do with it? I know this Qn is 8 times Qn minus 1 plus Qn minus 2. So this fraction can be written like this. This is trivial. But I can divide both top and the bottom by Qn minus 1. And I would get this. Same kind of expression, but then n1 lower. So I can repeat this. And I get a finite continuous fraction expansion. You can do it. You can do the same trick here with Qn minus 1 and then repeat it till, boing, it stops. I get this finite expansion. Oh, and note, this is very nice because this is like the past at time n. And this is what you just saw, an. And then the moment before that, you saw an minus 1. And the moment before that, you saw an minus 2, etc. Let me do it up to the beginning a1. So this Qn minus 1 over Qn, this is like our past at time n. And we just saw the digit an, and the moment before we saw the digit an minus 1, and the moment before an minus 2. And by the way, if I apply t n times 2x, this is which starts with the digit an plus 1. So this is the future. So this expression has in the t's the future of x at time n, and in this fraction Vn the past of x at time n. So it's like two-dimensional in a way. It has both future and past inside. Oh, that's nice. So I could sort of write, if I sort of assume I keep my x fixed, Tn is the future n, and so this is this expansion. And if n is 0, it's just the expansion. This should be a point comma. And so a1, a2, etc. And the past. So v is 0 if n is 0. There's no past yet. It's about to start. And then, you think like, okay, this Vn is clearly in 0, 1. So if I do it to the T and Vn will walk around in the unit square. That's sort of a nice thing. And I see, if I write this abbreviation, the Tn was Tn times applied to x, I get this expression. So my approximation coefficient, which was Qn squared times, in absolute value, x minus Pn over Qn, is actually this number, which depends on the future and on the past. Nice. And actually, I can get the previous one as well, because Tn is 1 over the previous one minus the digit. So you can rewrite it as Tn minus 1 is 1 over an plus Tn, and plug it in. And what do I find? Well, of course, theta n minus 1, the approximation coefficient at time n minus 1 is same formula. But then I start to plug in. So I replace Tn minus 1 by this guy, and then I see, oh wait, I can divide out, and I find, this is annoying, I find that it's actually going to be Vn over Tn Vn. So actually, if I know time n with my future and my past, then I have both approximation coefficients, the theta n minus 1 and the theta n. That's sort of neat. Now, so you sort of it's sort of natural to work on the unit squares, 0, 1 by 0, 1. And that's something which Hitoshi Nakada from Keio University, still active, still alive, did in the 1980s together with Ito and Tanaka. But he did this is his thesis, his PhD thesis. He looked at what is called the natural extension. So let's call this omega 0, 1 by 0, 1, the unit. On this unit square, I define a map T. It's like a calligraphed T as follows. On the first coordinate, I just do the regular continued fraction map, the Gauss map. And on the second, I sort of keep track of what I've seen. So if you repeat this map, your past will sink away. So if you start with X, this will be A1. But if you repeat it again, you get 1 over A2 plus 1 over A1 plus, if you start with Y 0, 0, but you can start with any Y between 0 and 1. So this is sort of, if I apply this map T n times to the point X naught, I get Tn Vn. Okay. And now, of course, I have to define what I do in 0. Okay, so I have this. And so I can say that if I'm between a half and 1, my first digit is 1. So I'm going to call this region V1. And then if I'm between a half and a third, then my region is, digit is 2. So this is V2, V3. V from vertical. Oh, by the way, the Tn and Vn are called the Dutch, the T from toekomst, future, and the V from verleden, past. So it also sounds good. I mean, that's one of the nice things. If you make something, then you're the first one, so you can. Okay. Now, suppose delta is the triangle with vertices 0, 0, 0, 1, and 1, 1. So simple triangle in R2. Actually, the interior of it. And in view of what we just saw, that we can express theta n minus 1 and theta n in Tn's and Vn's, it's natural to define a map from 0, 1 by 0, 1 to this triangle in this way. So this would be like theta n minus 1 and Tn Vn, and this is theta n. So actually, I sort of right away see that theta n minus 1, theta n are in this triangle. The square is mapped to that triangle. It's a calculation. I'm not going to do it now. But I see this. And then I immediately have a valence result. And actually, what is really nice is that this is a bijection. So I can also go back. That's really very nice. So it's not just some map which might pile up things on top of one another. And that is not happening. It's sort of a unique thing. It's a bijection from the unit square to this triangle. So I can go back and I can sort of, this is a calculation. It's in one of my first papers. I think the one with my advisor, actually. It's a calculation. You can see what the inverse map is. It's not so hard. It's just, a trick, really. Okay. And you might think, why is this interesting? Now, note that I had these vertical strips. And under this map, the first vertical strip is mapped to this triangle. And the second vertical strip is mapped to this, what is called not a rectangle. Right, indeed. And then the third one like this. And they're sort of split upon... the first one is actually also one, but this straight line, and that's why you see a triangle. But in a half, actually these two lines sort of become one. That's why you have a triangle, and the rest is not triangles. So you could also say, what if I start with a theta n minus 1 theta n? Go back to the unit square, apply my map T, and return here. Oh, that's sort of possible, right? I mean, I have a bijection psi, so I can also have a psi inverse, which is a bijection. The T, the calligraph T, is also, apart from a set of measures 0, a bijection. So everything is actually a really beautiful world. So, Oh, by the way, because the theta n minus 1, theta n are in this triangle, theta n minus 1 plus theta n is going to be smaller than this line. This is the line x. Ha! So the sum of two consecutive thetas is smaller than 1. So the minimum of 2 is at least smaller than a half, because if the minimum was larger than a half, then the sum would be more than 1. So we immediately have found that the minimum of two consecutive ones is smaller than a half. Right away, this whole setup throws this out like that. And well, we can also define horizontal strips, and well, these are the vertical strips you just saw in the picture, and vertical strips are mapped to the horizontal strips, etc. There's a lot of knowledge in here. If you're in a vertical strip, you know that the first digits of your first coordinate is A, and if you're in a vertical strip, that's your future really. You see, if you're in the first one, let's say from 1/2 to 1, your AN plus 1 is going to be 1. And if you're in a horizontal strip, actually you're looking at the past, the first digit. Okay, but because of we can map such a vertical strip to one of these guys I just showed you. You can easily show that these guys I showed you have a very nice structure. What are these guys I showed you? Let me just show you again, because it's going perhaps a little bit fast. So the V1 is mapped here. Okay, this is not really a quadrangle, but okay. The V2 is mapped to this one. So with vertices 0 1/3, this is 2/3 1/4, etc. So it's an easy calculation, really easy. All the calculations are sort of easy. So I find that these guys look like this. And the other ones are the reflection in alpha is beta. And now I'm going to define a map F from the triangle to the triangle in what you would do. And you just take the inverse, or they should be capital letters. I take the inverse, I apply my map T, and I go back to the triangle. So these should be capitals. I will change them before I send you the slides, the Beamer presentation. Okay. And of course, if you have a theta n minus 1 theta n, then you map to theta n plus 1. So if you know what the inverse maps are and just plug in everything, it's really an exercise. Well, actually, it's in a paper, but nobody did it, so I could publish it. You can sort of show that this F alpha beta, if I just take any point alpha comma beta in a triangle, is mapped to this guy. So I know now theta n minus 1, which is the second coordinate, in terms of the first two coordinates. I have this expression. Let me just show you. And actually, I also have the other one around. Well, this should be a minus 1. So this is a theta n minus 1. This is a typo here. I should have a minus 1. But so I can, if I have two thetas and I know what my expansion is, I know what the next one is. That's very nice. And from this, you can sort of say, okay, what are special points? Well, points which are sort of fixed under T. So they go like the golden mean, like root 2 minus 1, etc., which stays under T on its spot. You can look two-dimensionally. They also stay on their spot. And what can you see? Well, they're mapped to, hey, this looks very familiar. If A is 1, this is the 1 over root 5 from Hurwitz. And in general, this is the one from the theorem I showed you. This is a fixed point. But then it's nice. It's really mapped to itself under F. It's a calculation. I'm not going to show you. Then you say, okay, let's look. Suppose I have a theta n minus 1 theta n. It's in one of these strips. Let's say in the strip where the digit an plus 1 is going to be A can be 1, 2, 3, 4, etc. One of them, so it's a fixed A. Well, then you can say, okay, what is the derivative of this function to alpha and beta? And both derivatives are, the map is going down. So you are in the really nice situation. Let me show you the picture again. Yeah, this is a little bit annoying, sorry. I should have put it twice. You see, in this strip, so A is 2. Here's the fixed point. And this map F is going down in the X direction and going down in the Y direction. So, and since this is a fixed point, you can sort of use to look at where is the minimum of 3 consecutive thetas. That's the way to do it. And if you do that, then bang, this theorem is proved. Okay. Let's see. This is all what I told you. Wow, there's a lot of telling. So this proves this theorem. But I didn't think about ergodic theory or probability theory or the relation with. And it says here, there is much more, indeed. And Yusuf can also tell you about that. Let me tell you a little bit, because it's already 1.5, a little bit about this much more. But in a way, what I'm telling you, it brings you up to the boundaries of what we know. Of course, a lot of these things have been done for other continued fraction expansions or other number theoretic expansions, but actually, there's a lot to be done still. So if you are interested, talk to Yusuf or to me. You can always send me an email or talk to me on Skype or whatever, Facebook, I don't know. So Nakade looked at 0, 1 by 0, 1, and he looked at the Borel sets. He had an invariant measure for this map T, this calligraphed map T, and he showed the invariant measure has density 1 over log 2, that's just a normalizing constant, times 1 over 1 plus and yeah, he was able to show that this is actually an ergodic theorem, a system. And this is this map we just saw. And what does it mean? It means that we can use the ergodic theorem, and the ergodic theorem is actually a hip version of the law of large numbers. So we can bring suddenly a lot of power from probability theory into this kind of number theory. And actually, Nakada's result, his paper, is really a starting point. It's really a major point in this whole field. And certainly in this, what is called metrical theory of continued fractions. And let me briefly outline a little bit what is this theory. So this theory started in 1802 and 1812 by Gauss. And Gauss showed that, or Gauss found the invariant measure for the regular continued fraction. And the invariant measure has this as density. This is simply the density Nakada found if you sort of project on the first coordinate. So if you integrate out y. So if you know a little bit of probability, you can sort of do that marginal, so to speak. That is this density. Nobody knows how Gauss found this. Nobody. It's a mystery. And actually Gauss noticed that if you look at the inverse image of an interval from 0 to x between 0 and 1, and you take the Lebesgue measure of this set, the lambda means Lebesgue measure. If n tends to infinity, I should have had an arrow here. This converges to this invariant measure he found. So it's really invariant measure. So actually Gauss saw that there's a convergence of measures. Mind you, Lebesgue still had to be born. I mean, Gauss saw this, and we talk about Lebesgue measure here, but actually Lebesgue wasn't even born at that time. And Gauss was interested in the speed of convergence. And he asked Laplace, like, could you please explore, well, it was a little bit cynical measure for you, for someone like you, it must be so easy to prove that, etc. Actually, it took more than a century before two people independently found the proof of this convergence and also found the speed. And then a lot of people worked on this. And then in the 1930s, this result was used to get a lot of properties of continued fractions. And then after the Second World War, Rilnacevsky used ergodic theory to find these properties as well, but he didn't find the speed of convergence. And then this sort of died out until the 1980s, when Hendrik Lenstra was working on primality testing. So a field you might think has nothing to do with this. And he came up with a conjecture which turned out later to be first conjectured by Döblin. You probably have never heard of Döblin. Döblin is one of the big treasures of mathematics. Some people call him Dublin because he became a French citizen, but actually he was a German who fled from the Nazis. His father is a very famous novelist who was a very strong anti-Nazi. And Wolfgang fled to France, became a student there. A lot of people think he was a student of Lévy. He wasn't, but he worked with Lévy. And he had many, many, many things, not just on continued fractions, but he sort of came up with the Ito formula in a very basic form before Ito, etc. Fortunately, he committed suicide. So he was a soldier in the French army. He knew what was coming, of course, because he fled Germany. So he fought in the first days of the Second World War in 1940. And when he saw that they were losing, he shot himself because he didn't want to go to a concentration camp. Fortunately, he had written down a lot of things and sent them to the archives in Paris. And later they were opened, and it was incredible what he discovered. Incredible, such a young man. But yeah, most people have forgotten about him. So this is the last thing I want to mention. What is the Lenstra-Döblin or Döblin-Lenstra conjecture, which was proved, by the way? Well, it's a kind of, how are these thetas distributed for almost all x? So apart from a set of Lebesgue measures 0, so of length 0, what can we say in general? What is the typical behavior? So you can look at how many n's from 1 up to capital N do we have such a theta n is smaller or equal than z for some number between 0 and 1, and divide by this capital N, and let capital N run. So you get like an asymptotic frequency. And Lenstra, I don't know how he did it. I asked him, he's still alive. How did you come up with this formula? He was able to say, to explain this distribution function. It's linear from 0 to a half, and that you can explain by Legendre, the one you just saw. And then it sort of slopes off because then the continued fraction map starts to miss some rationals. That's the explanation. So from 0 to a half, it picks up all rationals which are sort of good, and then it starts to miss. So this is by Lenstra. There are many people who sort of try to prove this. For instance, Knuth, the guy who came up with LaTeX, or TeX actually, he tried to prove this. He didn't succeed because he wanted to prove it using a one-dimensional system. But the problem, as you saw, the theta is essentially two-dimensional. They have a future and a past component. So you need a two-dimensional system. And at some point, Nakada published his natural extension. And then my advisor, together with two students, these were just master students, Wie Bosma and Freek Wiedijk, well, they were able to prove this conjecture, actually. And so this is really nice. And it's actually not really a difficult proof. But their proof is what Nakada did, doing it two-dimensionally. Okay, well, and then, yeah, well, from this you can do many things. You can look at other continued fraction expansions. There are very many. The most important one is the regular, but there are really many others. And you can ask for more properties. So this is something which is a growing thing today. Fortunately, otherwise I wouldn't have a job anymore. So there's really much more to do. Okay, thanks.
Okay, thank you so much, Dr. Kaur, for a very intriguing presentation.
I hope so.
I personally didn't know that fraction can be surprisingly interesting and elaborate. Like,
nice.
okay, so I think we already have 3 students lined up to ask you questions directly.
I see also chat, yeah.
They are Nisa, Thomas, and also Tegar, if I'm not mistaken. So, opportunity to Nisa.
Yeah, that's good.
Nisa, are you here? No? Okay, so I'll give the first opportunity to Thomas. I believe Thomas in the room. Student.
See somebody in the car.
Yeah,
Check.
someone's driving.
Check myself.
Thomas?
Iya, Pak.
Thomas, can you hear us?
Yes, sure.
Okay, so go ahead.
I was scared to wait.
Hello, sir. My name is Thomas, and I'm from third semester student at Sriwijaya University. And I want to ask about what's the meaning of Mobius transformations and what's the connection or correlation about fractions expansions. Thank you, sir.
You have to sound?
Let's use the TV then.
Oh. Please move your mouse.
Sorry, Thomas, can you question one more time? And first introduce yourself. Thank you.
Okay. Hello. My name is Thomas, and I'm from third semester student at Sriwijaya University. And I want to ask about what's the meaning of Mobius transformation and what's the connections or correlation about fractions expansions. Thank you.
Okay.
Okay.
Should I switch off my own sound?
Yeah.
Okay. I'm being muted. I need to switch. Okay, the idea is really that this map is 1 over x minus an integer. You can write it as ax plus b divided by cx plus d, and then you have to choose the a, b, c, and d. And that's the idea, really. And then you can sort of use matrices and use linear algebra to get results, actually, like I did. And so this gives you a way. You don't have to. I mean, there are other proofs, but this is a way to use linear algebra to make things easy. And for instance, you had these matrices A1, A2 up to AN, 0, 1, 1, digits AN. What is nice is that the determinant is -1. And then if you take the product, the determinant will be -1 to the power n. But this product was Pn minus 1, Pn, Qn minus 1, Qn. So then, because the determinant is Pn minus 1 times Qn minus etc., you right away know Qn's are relatively prime. So the reason to do this really is to use linear algebra, to use results from linear algebra to prove things. And by the way, there are two. This is just the one-dimensional map, right? But you have higher dimensional generalizations of continued fractions. These are called multidimensional continued fractions. It's a little bit stupid, or Jacobi-Perron expansions, and then you use 3 by 3, 4 by 4, 5 by 5 matrices in sort of a similar fashion. Fortunately, the world of continued fractions is very nice, very beautiful. The higher dimensional ones, it's really bad. So people really worked extremely hard. I mean, already the idea that Jacobi and Perron worked on this, Perron had it in his PhD thesis in 1900, that people like that, incredibly powerful people, worked on this and didn't do the same kind of results as for the regular. Tells you something that the problems are very difficult. So what you would like is, if you have a vector of irrationals, to approximate that by a vector of rationals. simultaneous approximation, as it were. There you can also use Möbius transformations, etc. Unfortunately, the proofs and the results are not as nice as for continued fractions. It's really a pity. If you want to read more about it, I would say you should read the papers in books. Schweiger from Salzburg, he's really one of the big experts. Or Valérie Berthet, so she is in computer science and symbolic dynamics, and she also is focused nowadays on multidimensional continuous fractions. They work very hard on it. It's very difficult. I gave up, to be honest. I thought for a time I could make some contribution, but yeah, unfortunately not. It's not so easy. It's really hard.
Oh, I believe so. It's really good.
Yeah.
Okay, Thomas, any follow up or? But I think that was very, very clear. Okay. The second one will have Tegar. Tegar, are you here or there?
Yeah, I'm like this screen because I look at an enormous screen where I see your faces.
Tegar, are you in the room or in Zoom screen right now?
Okay, sir. Thanks for the
No.
time. Let me introduce.
Okay. Here we have Tegar.
Okay, thanks for the time. Let me introduce myself. My name is Tegar Ahmad Abibi and I am from Mathematics Education Sriwijaya University. For the first, can you show page 27?
Oh, page 27. I have to share my screen again. Share, yeah, that works. And now I have to go to 27. I don't see the thing to the right. All the faces are in front of it, so this is a little bit annoying. Can I move this a little bit aside? Yeah, it works. 27. Oh, wow. 7. Sorry, it goes a little bit slow. 27. Yup. Yeah. What is your question?
As we know, if f0 is it mean the value of the function on 0. But in this page you wrote m0. What is it mean?
Oh, well, Mn is a matrix. So we saw that's the matrix R, Pn minus 1, Pn, Qn minus 1, Qn. And I apply this matrix to the number 0. And this means what I defined as a Möbius transformation. So this guy. So if I have a matrix A of x is, and if the matrix is A, B, C, D, it's going to be A times x plus B divided by C times x plus D. So if I do Mn, let's see, where is it? If I do apply Mn to 0, I do Pn minus 1 times 0 plus Pn divided by Qn minus 1 times 0 plus Q is Pn over Qn. You see? So that's what it means. So that's why I wrote that here. Well, I didn't write it out yet, but at some point, some place it's written actually. So this Mn0 is actually the second column as a fraction of Mn. That's the idea. I don't know if you see this, but I get it's a very annoying, this black thing all the time there. It's sort of hiding it, but that's what it means actually. Does this answer your question?
How could m0 equal to 0?
Say it again.
How could m0 equal to 0?
0? M0 the matrix. Yeah, you could call M0 the identity matrix 1, 0, 0, 1. Because then, if you want, you can do this whole thing for general axis. And so if x is some number in R, then you can look at A0 as the first digit, so the 0th digit, and that's such that x minus A0 is in 0, 1. And then you could say, okay, my matrix A0 or M0 really is going to be 1, A0, 0, 1. But since I'm working between 0 and 1, I don't have this problem. I don't need to do that. It's anyway 0. But you could do it in general. You could do it for any x, but since if you have an x, let's say between 2 and 3, I can slide it by subtracting 2 between 0 and 1 and do everything there. That's so I down. But yeah, you could do that. Yeah, definitely. And then a0 apply to 0, 0, of course. Yeah.
Okay, Tegar, do you have a follow-up?
Okay, thank you, Mr.
Was that clear?
Yeah.
Good.
All right, thank you, Tegar. Is Nisa with us now?
Yes, yes.
Oh, I should suppress this. Am I share? That you can see it.
Nisa?
Yes.
Hello.
Yeah. Yes, sir.
Okay, she's here. Okay, go ahead.
Okay. Let me introduce myself first. My name is Anissa Ramadana. I am from second year student of Sriwijaya University. I feel so interested with decimal expansion that have been described earlier. Start from the decimal on Tewiklingen until the last one, Lestra Dublin. And my question is, does P have finite decimals or is it destined to be infinity? I hope I can get the answer. Thank you.
Fine. Okay. Oh, sorry. He is Dutch. That was a system. Okay. Well, to be honest, P is one of the different numbers. We know a number of its digits. The continuous fraction digits. We know a number of its decimal digits. But that's it. We don't know them all. Funnily enough, the number E, 2.7, etc. We don't know all its decimal digits, but we know all its continued fraction digits. We know exactly the continued fraction expansion of E, not of pi. Pi is somehow more difficult or random, but E is very well behaved, surprisingly. And I can tell you a little bit more about it. Yusuf and I have a paper on these numbers. You have numbers which are quadratic irrationals. So they're like a plus the root of b divided by c, and a, b, and c are integers, and b is a positive integer, which is not a square. So it's not like b is not 25. So this is an irrational number. And then the continued fraction expansion is actually from some moment on periodic. It repeats itself. Okay, that's a result by, I think, Legendre. Oh, no, sorry, and by Euler. I mean, really big shots worked on this. And then you can also show that E, which is not a quadratic rational number because it's actually transcendental, has a kind of weird kind of periodic thing. It's periodic, but the numbers in the period, they're not steady, but they blow up. But you can describe them completely. So pi is very difficult, but E is much easier, surprisingly. So yeah, sorry. There are many numbers. We have no idea how they expand it. Actually, this is one of the reasons why Jacobi and later Keguruan look at higher dimensional continued fractions, because they wanted to look at the action of algebraic numbers, which are not quadratic but higher order, order 3, 4, etc. So that's why they started to look at these multiple generalizations to get a grip on them. So.
Yeah, maybe Nisa can be the one who actually find the periodic or the finite number of decimals of pi someday.
Oh, yeah, I have no idea. That would be great. Well, there's so many questions.
Yeah.
But already was root 2 minus 1 to find. So people think it's going to be. They think there's no idea. So yeah, this is a really exciting field to work, I have to say.
Okay. Nisa, are you satisfied, or do you have any follow-up?
Yes, I satisfied.
Oh, okay. So no,
Okay, maybe we have another question, maybe from the lecturer. You can ask question, right? From lecturers of Sriwijaya University. If you have any question, then you can ask directly. I'm a little bit intrigued with the expansion that you explained earlier about unit expansion. So it's 1/4 can be 0/2 and then plus, etc. My question is, do you mean that a fraction can only have one unique expansion, or there's more to that, or
yeah. So like 1/7, if you look at the decimal expansion as a unique expansion, and it begins, and at some point it will be periodic.
Okay.
And a quarter, which is 0 to 5 decimal expansion, can also be written as 0 to 4, and then all nines. So it has 2 expansions, not unique. So if it's finite, you can also make it infinite. The nice thing is, if your base is not an integer anymore, not like 2 or 3 or 10 or whatever, but a number just larger than 1, not an integer, then you will have infinitely many expansions in that base.
Okay.
So that's really a spectacular, I mean, it's really, if you change your base to any number larger than 1, which is not an integer, it's loose. I mean, really, it's incredible. Then suddenly, yeah, a lot of people working on this because it gives you the option to have more than one expansion. So if you make a mistake in reading digits, you can sort of try to fix that, which is impossible with a decimal expansion. If you have an irrational number and you read one of the digits wrong, then it's over. It's wrong. It's going to be wrong. But with non-integer bases, then you might have a way to fix it. And there are a number of people working on this. One person who is extremely famous is Ingrid Daubechies. She's a Belgian lady who works in the United States. And a number of her students work on this. And this is AD conversion. So from an analog to digital signal. If you want to convert an analog signal to digital, they prefer use non-integer bases because then you can sort of fix mistakes. That's the idea. They have a number of papers on that. So, but I mean, if you want to know more about that, I would read them. It's actually very readable, very nice stuff. Yeah.
Well, funny enough, it's actually answer one of the big questions that maybe a lot of students ask. What's the use of mathematics in daily life? So you have it.
well, you know, when I was young, everybody said, what's the use of mathematics? The only kind of thing that you guys do is making exercise.
Making life right now.
Yeah, I have a job. Guys, we were lost. Sorry, we were lost suddenly.
I thought we got kicked out. Okay, it's 10:58 now here. I think that was the last question for you. And I believe we have certificate of appreciation for Dr. Kaur, maybe Professor Yusuf Hatana can present the certificate. Ari, can you display the certificate, please?
Oh, that would be nice. Great. I will put it in my office. You've been in my office, right?
Yes. But I don't think they have the print.
Oh, I'll just send it. Just print it and I'll put it in a frame.
Here's Dea, maybe, or Novika.
I see people talking.
Yeah.
It's very funny. This is a typical online thing, right?
Technical difficulties.
Well, 2 hours. Not so bad.
Okay, while we're waiting, maybe you can try to tell us about your last publication with Dr. Hartono. I believe you, I understand you. Oh, this is the certificate?
Oh, wow, nice.
Okay.
Oh, nice. Yeah. Oops. Yeah. Wow.
This is the certified for Crime. Am I saying that right?
Sure.
As the guest speaker of our general lecture. Thank you. Give big round of applause, everyone.
Thank you.
I hope this won't be our last time to see you speak in our university.
Oh, that would be nice. Yeah, definitely.
We'll talk later.
Yeah, sure. Okay.
Okay, I think that's all for us here. So I'll get back to the Master of Ceremony, Miss Chichi Ratnanenchi. The time's yours.
Okay, thank you very much to Mr. Dr. Kor Kraikam for the very insightful knowledge, especially for us as the students of the Department of Mathematics Education. And also thank you to awesome moderators, Professor Dr. Yusuf Hartono and also Mr. Jerry Araiko MPD. Alright, well, ladies and gentlemen, to end today's general lecture, let's say Hamdalah. Our highest appreciation is given to all participants of today's general lecture. I am Cici Ratnanenchi. Thank you and see you. Wassalamualaikum warahmatullahi wabarakatuh.